make it pretty easy. We're going to talk about R, L, oh, come on, and C, how they play with each other and what they're useful for. And what you'll find is that L and C only really matter for alternating current,
Uh-huh.
but the resistor matters for AC and DC. Okay.
Right.
So,
Hold on, let me get some paper and stuff going.
gotcha.
Why would you email me now and respond to this email, apparently?
So who is it?
It's emails. Okay.
And making sure there's no one else in the meeting room that I'm missing. I don't think a lot of people are paying attention to the fact that I have started.
Oh, and also apparently, like, my grandmother absolutely needs like live-in help and refuses it. So no, nobody, like, oh, whatever.
That's bad. I'm really sorry to hear all this, Sarah.
It's okay.
I mean, if there's anything I can do other than just like, help with physics, let me know. But,
Convince the woman to like have a live-in caregiver.
I'll try.
Yeah.
Get me in touch.
Oh, it's just ridiculous. But anyway.
All right. So, are you
Yeah.
able to
This.
focus enough to? Okay.
Okay. So I'm still rather confused. So according to the loop rule, right, all the voltages have to equal 0, basically, right? Loop is 0. But, so I like, so I did that. And, for me, like the voltage of the battery is 34. So everything has to add up to 34. But, so, and I found like the voltage of the first resistor that was not in parallel of anything, which was about 18. So, I subtracted those out somewhere, and got, what the entire voltage of like the whole thing is, like the whole subset of like parallel guys. So those are like 15.7. And he was like, yeah, so that's the voltage of each one in there. That doesn't make sense.
Okay. So, I'm going to start from some first principles a little bit and work through it so that I think it'll make sense a little better. Because as I understand it, you guys haven't really done first principles. You've only had like, minute physics and like crash course videos.
Yes, those don't help. Like, it's fun to watch. It makes me feel productive. But did I learn anything? No.
Okay, so that being the case, let's think about like, I'm going to record this. Let me start recording this, by the way.
You are. I see the little red dot.
Okay, so I am recording it.
I mean, it says so.
Yeah, I see that too now. Okay, so let's start with first principles of circuits.
Okay.
And this should cover pretty much everything we need until we get to inductance. Inductance is going to need a little magnetism.
And that's the next chapter. So we're coming up on that.
I'll do that tomorrow then, if you have a day before or something. So first principles of circuits, we have two types of circuits, DC and AC. And what those mean is direct current and alternating current. And it turns out that it's really more the alternation of the voltage, not the current. So to red, this is represented usually with a battery. Battery, the current flows from negative, flows from just like in chemistry. Okay. So it flows from positive to negative. Though in reality, if we're talking about the electrons themselves, the electrons come from the negative side and they go to the positive side. So if this is sort of a convention that things go from positive to negative. The idea, sorry, what?
Does it like matter? Because I know like we have to, trace around the loop like in a certain way. But like, does it matter technically which way it's going, or?
So the convention is really sort of important later on when
Okay.
we're talking about magnetism. The current flows positive to negative. The thing that is actually flowing is the electrons. They flow from negative to positive. So conventionally, we say current flows from positive to negative. This can be very confusing for a lot of people. But think about it as positive as being uphill and negative as being downhill, like I did in my last little video I uploaded. And a positive ball is what we start with. A positive ball is going to roll down the hill. So it's going to roll from positive to negative. Okay. So this is the idea you should have in your mind, where this is 0. So that means an electron is going to follow the exact opposite rule. So for an electron, you can just flip this whole thing over and get the same idea. And the thing that's flowing, like I said, is electrons. So when we talk about, for example, electromotive force and things like that, the thing that is applying a physical force to the resistor that is causing it to generate thermal energy is electrons, not protons. There are conductors we can create that do have positive charge, so positive ion flow, but those are generally crystal semiconductors where we have like a proton at the end of an inorganic molecule, and we're using that.
Okay.
So that would be something like an ion conductor. You can look up perovskite crystals. That's actually what Dr. Covell does, which is why it's frustrating that he hasn't talked about this to you guys. Studies perovskite crystals, where you have a crystal that creates an internal potential and the positive charges are what flows through it. Okay, so then we're going to talk about alternating current, which is generally written this way, little wave in there. And I don't know if you guys have done a lab where you could use a fake oscilloscope yet, but an oscilloscope just shows you the waveform of the current. So the current is essentially a sine wave for most purposes. You can get a square wave or a sawtooth wave, which is like this, and this is square, right? You can get those, but it turns out that these are actually the sums of different sine waves. So I can take an infinite sum of sine waves, or as large as I can to get the precision I need, and get a square wave and a sawtooth wave. That's called Fourier composition. So I'll write that down. So every single thing we do in current, right, is either DC or AC. DC is kind of fucking boring. Stuff goes in, does work on like a light bulb, which acts like a resistor, or like on a motor, which acts like a resistor, and then it comes out. Okay. For AC, the change in the current is actually the important part. So that's why resistors are over here. And for 291 and for 211 and 212, you're probably going to mostly deal with DC and touch on AC to understand the components. But this is resistors, and this is RLC over here. So this is R3. Right, so if I draw a circuit, I'll change my color here. If I draw a nice, pretty alternating current circuit, I got my little alternating current generator. And in real life, we have to generate these using usually a chemical potential. But with these, we can this is why all of our power is run by motors. We have a magnetic loop that is basically turning in a circle, or we have a loop of wire that's turning in a circle in a magnetic field, and that's enough to generate power. So that's how we generate current. And that's why alternating currents are sine waves, because if I'm rotating something, right, I get a sine cosine.
Yes.
You see what I'm saying? Yeah, so that's actually where you get into Lenz's law, which we're going to talk about probably next video as well, because it goes with inductance. But
Okay.
today we're going to keep just on circuits. So I've got my circuit here. These are the classification parts. So we've got DC and alternating current. And so DC and AC, and then the other classification that we need to be concerned with, and I will clear out a spot here for it. I love this thing. So much better. I'm literally using like a pen. But so then the second classification is series or parallel, though this is technically a sub-classification because we use series and parallel to do different things. I can use a series or parallel circuit to get the thing I want. And this is what electrical engineers and electricians spend years of their lives learning how to do, is how to use series or parallel, the sub-classification here, to do what they want with their given power source. Right? So I can have either one be a series or a parallel. Those are our four classificatory ideals here. So we've got these two species of circuit, and then these I call these subpaths because they are not a complete circuit. A circuit is only a circuit if it stops and ends at the same point. Okay, so let's move on to the next thing. I will clear my drawing. Does anybody else want to look at this for a second? Okay, I'll clear it. Okay, now we should move on to talking about DC parallel and DC DC parallel and DC series. Okay, so what I've got here, there is sometimes a capacitor in a DC circuit. The only reason that a capacitor is in a DC circuit is to smooth the current, basically. So if I look at a waveform of what the current is doing in a DC circuit, it looks like this. And if I suddenly turn it off, it goes like this. And this can damage components. So sometimes we'll do something like this. Right, so there's my capacitor down here. And then here is my resistor, or whatever component I have, right? So my current is flowing through, and it's going through the resistor because it can't actually pass through the capacitor, right? We know what the formulas are for capacitance. I talked about those in another video. But so it can't pass through the capacitor because it's just generating basically a sort of buildup of charge on the capacitor. And as soon as I turn it off, what the capacitor lets me do, so this is here. And then this is with capacitor. And it looks like this. So the reason it kind of smooths that harsh edge there is because all this built up charge right here, which is built up by this voltage, is then released back into the system, flow through. And it flows through basically with like a more smooth waveform. So depending on the strength of the capacitor, you can get different sort of curve smoothings here. And we'll see basically the reverse effect with an inductor, which we'll talk about in a minute. So let me erase, let me move on to parallel. But first, let me write down the formula. So the change in the voltage drop over a resistor over here is equal to the current, which is a constant, times delta R. And I'm going to repeat that. Current is a constant in this circuit, in a parallel, oh wow, I have these written backwards. I am so sorry, everyone. I was like, I said that for like 10 minutes and it was backwards. Let me make sure that I don't do that again. Oh my gosh. Yeah, if I say something that seems backwards, please tell me. I know that you guys have a little bit of experience with it, but we are not infallible, those of us who teach this stuff. So I'm going to erase one more thing. Okay, so we're back at our little like series circuit here where the voltage drop over each resistor is equal to the current, which is a constant, times the resistance of that resistor. Okay, so, and we will get into this a little bit, but this also lets us talk about another property of these, which is the idea that for most circuits, they can be represented as a series circuit with like some sub-parallel paths. And so that means that the current in to a point, no matter what happens in between it, has to be the same as the current out. We call that the node law or the node conservation law. I forget.
Is that the same as the junction rule thing?
Sort of, yeah. It's like the current in, so I in, has to be equal to I out, unless the electrons themselves are being used by something,
Okay.
which doesn't happen,
Oh, cool.
right? So look at me, doesn't happen, right? We're talking about, this is physics, not electrical engineering. It can happen with semiconductors and things like that. We are not concerned with that. So the current in is the current out. Okay, so I will then talk about a parallel circuit where delta V is not necessarily equal to delta R. And then we'll talk about how we can then picture them as being the same, right? So we've got resistor 1, and then here we've got resistor 2. And they have what's called the property of harmonic addition, where I'm going to write this with this form right here. This is a common form for an algebraic sort of operation that we don't know what it is. Bless you.
Thank you.
And what it looks like is 1 over R1 plus 1 over R2. So that's what this is defined as. There is an inverse operation for alternating current that we will talk. I might not ever even get to in this class because it's complicated. It involves imaginary numbers and stuff, and I don't think you guys actually do that for your homework.
What's that symbol?
So this symbol is just an algebraic stand-in symbol. It means I have this operation. I don't know what it is or what exactly it does until I define it, but it's, you know, it's shorter than writing this out. So I could write this out every time, or I could associate this with this symbol and just know to do this with this.
Okay.
And it's commutative. If I do R1 and R2, obviously, since this is commutative down here, it doesn't matter. It's associative because if I have R1, R2, R3, then I'm just adding more terms under the divisor or under the division line. And if I, so we have associativity, commutativity, distributivity. You see what I'm saying? So it algebraically can be defined the same as like addition, but with a very different outcome of operation. With some properties that we need to maybe be careful with, because like, if they're both 0, this is undefined. So two open circuits obviously is the same as a single open circuit, but the operation of the resistances of those wires is undefined. Or sorry, not open circuits, open paths. Right. So an open circuit is technically got no current. It's like leaving the door open, so the wall is not continuous, but if the door is closed, the wall is continuous. That's how we think of open and closed. And it actually looks like that. So let me write that in here too. I'm going to actually clear this and do a new page. Okay. Circuit symbols. And I don't know if he's given you an actual lecture on this or if you've seen this somewhere. This is standard everywhere for a resistor. And in fact, there are sometimes variable resistors. So I can, for example, have you ever done a light bulb where you have the dimmer switch? That's a variable resistor. So it's drawn like this. So it's a resistor with an arrow telling me how close to straight my current is. If it's at 90 degrees, nothing flows. If it's exactly parallel, everything flows. So you can think of it as like, basically how far forward this is how much current is flowing through. Okay, let me show you colors. It's my favorite color, this weird magenta one. So then we've got capacitors, which generally look very similar to a battery. So a lot of times to separate them, we will draw a battery differently, and I'll get to that in a second. This is a capacitor. Sometimes you'll see them written like this in older circuit diagrams. Right, so these are equivalent. There's a few other notations. I think there's like 10 different electrical engineering notations depending on like what organization you work for and whether you're an electrician or an engineer or an electronics person. And so we're just going to go with the standard physics, which is literally the one on the left. I will always write the one on the left and circle it, and that will be the one that we use. And then we have batteries, which look like this. And I drew them like this before with one side exaggerated. What we will often do is actually do 4 so that it's very clear that we have a battery and not a capacitor. So I'll do 4 lines like this, even though that's really bad. These are equivalent. And I'm going to circle this one just so that you guys know to use this one to clarify. So it's 4 lines. Okay. Move on to AC power source. Looks like this. And you'll also see like something like this sometimes. Okay, and then I've got one last one, which I'm going to do here. I'm going to draw a box, and I'm going to make that here. And so then this last thing that we are going to need that I think is pretty interesting and important is an inductor. An inductor is very specifically drawn. So an inductor is one of the only ones that doesn't have a very like other symbol for us, is this. So notice that the loops overlap. If I roughly draw a resistor, I want to make sure it does not look like an inductor, because all of the information in the circuit can be given by the circuit diagram. I can also draw it algebraically, right? I can write everything out as a bunch of sums and series and stuff, or I can just look at the diagram and know what's going on. It's great. So we can also see it written every once in a while. I told you there's a second symbol like this, but I'm going to just specifically cross this one out because that one is always confusing and bad, and we're not going to do that. But it exists, so you might see it if you're ever looking at an old circuit, especially in like old science textbooks. So this is an inductor. These are the basic circuit components that you're going to be dealing with in your class. Are these, and anything that is adding basically load to the circuit is a resistor. And then these acts, the capacitor and the inductor act to do different things with change in current. So I'll explain that when I get to them, but they alter the way that current changes. They don't alter the current itself necessarily while the circuit is in DC flow, but when it first starts or stops, they alter it. So I'm going to clear this, and I'm going to do a couple circuits, and we're going to talk about them. Okay, so then we're going to start with, here's my circuit 1. Okay, we're going to do DC, so this is just resistance. Already your brain should be like, yeah, resistance. I'm going to have and this is messy, and of course it's messy because I'm trying to make it a challenge problem. Okay, so this is our baby circuit problem. We're going to call these R1, R2, R3, R4, R5, and R6. So there's a few things we want to know about this. One is, I'm going to write these down and see if anybody can answer them. What is the total resistance And we're going to do it algebraically, because algebraically should clarify this. And we'll call this V right here. This is negative, positive. So just so you know, the current flow direction does not affect things like this. If we have the current flow direction positive or negative, it doesn't affect resistance. There are a couple things you may learn about one day especially if you're in neuro and stuff like that, where you have like diodes or things that act like diodes. So those are generally written like this, and we will not deal with those here, but they exist, and I think it's good to know about them. And so all this tells me is that current can flow one way and not the other. So I can create what's called a full bridge rectifier, where it basically turns AC power into DC power. And it looks like this, where I have the backwards facing diodes that let current through when there is, oops, I wasn't gonna do that. That they let current through when there is negative current, and I have my forward facing diodes that let current through when there is positive current, and I did that back. And you'll notice that all four of the arrows point to the same like general node, and there's a reason for that. This is a full bridge rectifier. This is a very specific kind of component. If you ever see this, you'll just look for the words full bridge rectifier. Don't look for the symbol, but the symbol is pretty recognizable. It lets the positive current flow through this way, and then the negative current flow through this way, and then so that I always get power being driven. Anybody, I'm going to give you guys a minute to work on this, because I have as long as we need. So I'm going to erase this full bridge rectifier stuff, and I want somebody to try and answer what is total resistance. And who all is here? Patrick, are you still there? There's only 2 participants. I think Patrick left. Okay. Yeah, so Sarah, take a whack at this. Just give me the algebra. Go.
Okay, so I have R1 plus 1 over R2 plus 1 over R3 plus 1 over R4 plus 1 over R5 plus 1 over R6.
Okay, so
A lot of 1 overs.
Okay, so we want to think about something here real quick. This right here, we can just sort of like treat as its own circuit for a second. So anything that's nice and simple and in series. I think what you said is right. I didn't get it all down. I'm sorry.
Okay.
But so these are sort of in series. So they're simple and we don't care. This is its own little complicated circuit. So let me expand that out. We'll blow that up. So if I draw this again, what I've got is nope, that was okay, so this is the same, this is identical. Would you agree?
Mm-hmm.
Okay, so this is also its own little complicated circuit. So let's solve for this branch right here. Okay, switch colors. So for this branch right here, what we can do is, well, that is also its own little complicated circuit. So whenever we have a parallel, we want to solve for those parallels, and then we want to solve for everything else. So we have 1 over R2, oops, plus 1 over R3. And I'm actually going to write that with our composition form that I showed you before. So going back to the drawing, I'm going to say R2. Now, isn't that nice? Isn't that easier? And then plus R4 is this branch, this RB.
Mm-hmm.
Okay, and then we have R5. So we're going to call this full system C. Okay, so do you see what I did here? Wrote that down as our nice little algebraic form. And I can actually unfold this now all. And you know how to do the algebra. So knowing what the symbol is makes just writing it down to like get your forms right when you're doing your work easier, so you have less math. So then I'm gonna move this over here. So we have R1 plus RC plus R6 is equal to R, right? So then we have R1 plus R5, cross, bless you,
Thank you.
B plus R6 is equal to, and that should be our final form, R1 plus R5. And then I'm going to do a parenthesis because we know that our properties we know our properties of this, what I can do with it. And then that's R2. And I'm going to do these in some brackets. Okay, so that looks good, right?
Mm-hmm.
And this is the short form to write everything down that we need. And like I said, this symbol right here, this circle with the X in it, is general. It's a general algebraic multiplication or addition. We can define whatever operations we want to be this thing. So we're defining it to be a harmonic addition, which is 1 over 1 over A plus 1 over 1 over B. And I'm going to keep saying that because that's something that we need to drive home. But yeah, I think I personally think that's a much nicer looking than the fractional form, and then just know what it means. And when you are typing it into the calculator, you can solve for each subcomponent, right?
Mm-hmm.
Okay, I personally think that that's good for circuits, for DC circuits, and we're going to move on to AC circuits here. This is, you know, we did a little bit of parallel and a little bit of series. I do want to, before we move on, actually, it just reminded me, I want to touch on one thing. Come on. There. So I'm going to change colors to not poop color. And we have, let's say we have a voltage source, just arbitrary, moving into some branch where I have a parallel circuit. And then these meet back up. Okay, so these are parallel resistance. There was a question that was raised, which is, what is the voltage here? I'm going to change colors, so I'm going to do that. So what is the voltage here? 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 And what are the currents here as well? I'm going to label these A, B, C, and D. And I'm going to label our resistors R1 and R2. When we're doing this, this is kind of tricky, and we'll also do the same thing for a little series circuit over here. You can... Okay, separate that down the middle. Okay, how do we want to start this? So we have our general voltage source V and our general voltage source V, and we know that it connects, so it doesn't really matter how or what else is here. We're just concerned with A, B, C, and D, and then over on this side, we are concerned with A, B, and C. I know I'm taking a while to get to the punchline because I'm hoping that you're taking some time to think about this on your own. But so I have voltage is equal to potential energy per charge, right? And so if I have a potential energy per charge here, then that potential energy for charge actually has to be the same at A and B. Like, we can think of R1 and R2 as being different slopes of different lengths, right? So R1, for back to our ball analogy, right? R1 is like this. And then R2 is like this. So you see what I'm saying? They may be like this, they may be different heights, whatever, but the idea is that going from the top of the mountain, where the top of my voltage source is, I'm going to change color. So top of the mountain where my voltage source is to the bottom of the mountain where my voltage source ends has to be from V to 0, right? So QV to 0, potential energy. Right? Do you agree? Okay, so if this is going from QV to 0, and we know that an open circuit, or sorry, a closed circuit, but with no resistance, has a effective voltage drop of 0, right? That we can also say that C and D must be equal to 0, right? Because these are now on an open circuit back to our voltage source. Okay. So if we look back at Kirchhoff's law, where V is equal to IR, we know that this node, the current is the same as this node. We know that by the node rule. We just said that. And we know that the voltage over here is V at A and B, and it's 0 at D and C. So we're given V equals IR. So now what we have is that V is constant because the V going in is the V that matters. Okay. So the V going in is the V that matters because outside it's 0. So the V is constant because the V is not being split. Think about if you run the circuit backwards, right? If I run the circuit backwards, these have the same voltage back to that source, right? Even though they meet, they have the same voltage back to the source. Same can be said over here. So if I run the circuit backwards, which we said the direction doesn't matter, then these have to have the same voltage back to the source because they're acting like one wire until they hit the resistors. Okay, so I'm really slowing this one down so that we can really kind of like dig into what we're saying. So the voltage across parallel resistors is identical. So the current has to change. So we say V, and I'm going to call this a big constant phi. It's equal to IR. So now if we want to solve for I, we get that phi over R is equal to I. This is for each resistor. And this is true because we know Kirchhoff's law holds. And we know that the voltage is constant by the symmetry that we just said. If I run the circuit backwards, then the voltage here and here is one wire, sort of, and then the voltage here and here is one wire in the forwards direction. So we know by that that this has to be essentially one voltage and this has to be another voltage, and that's V and 0 or V and 0. Okay, by symmetry. Okay. So we know that I is equal to phi over R. And that's true for every single R. R1, R2, R3, R4, right? It's a little unintuitive. It takes a minute to kind of like think about it. But if you think about it as if it were water, the potential energy of a single drop of water at one side of a waterfall and at the other side of the waterfall has to be the same no matter which waterfall route it takes. So what the current is can essentially be thought of as the rate of flow through that side. So the rockier, nastier side of the waterfall is going to have less flow than the straight drop. The rockier, nastier branch of the river is going to have less current than the big, wide, deep side of the river. Okay, so that analogy of a river is one that I almost always go back to for electricity for people because it's kind of like intuitive, it sticks. But so this is important because this has popped up from a few people as well. Okay, now we can look at the series and think about this in the same way. We already said that delta V is equal to I delta R. I've said that in 2 videos now. So when I say delta R, I just mean each R. So in this case, over here for the parallel block, going back to that for a second, we can say with some like very distinct certainty, oh, come on, that I is not a constant inside my parallel universe here. I call it the parallel universe because it's, but I is not a constant here. It's a constant at this node and at this node, so we know I1 plus I2 is equal to I net, right? So this is like, I1 plus I2 is I net, but it's not a constant over each resistor. Now for this one over here, we actually have V equals IR, and I is a constant over each resistor because they're in series. So the reason is we don't see any big bunching up of particles. We don't see any like really strong magnetic or electric fields coming from certain parts of the circuit that we don't from others, unless we have an inductor, which is an AC thing. And that means that there can't be any bunches, so everything has to be flowing through relatively evenly. We can think about it, pardon me, we can think about it as if our battery here, right? Our battery only sends out enough that it can get through at a time. It starts off essentially knowing what it's going to be able to get through. So in that way, I almost think about it as the plus charge pulling the electrons through, and a resistor just adds weight. Right, so like it's like pulling them up in a bucket, and we've just added a bunch of weight to the bucket by adding a resistor. What is physically happening with the Drude model? The Drude model is I don't know if you saw that video. Okay. So the Drude model was that we have a bunch of electrons traveling like an ideal gas through a pipe. And they are hitting things and scattering off of them, but they are still being driven forward by the electromotive force, which is also the voltage. So in this case, we really, really want to think of the Drude model when we're solving for this kind of problem. I think it's only Sarah right now, so I think I might wait for her to get back. I'm sorry to anybody watching this video later, but you have to give me about 30 seconds. Okay, so we're back. I took a little break for those watching the video in the future because we only have one person at the help session, and I wanted to make sure that she got what she needed. So we've got this sort of like little series here, and what that tells us is that R1 plus R2 plus R3 ... is equal to our total resistance. So we can say that our voltage is equal to IR. is equal to I times the sum over the indices, and I'll use I just for that, of Ri. So this is just saying I have the ith resistor plus the jth resistor plus the kth resistor plus the lth resistor. Each resistor is added. Now if I have like this, I can actually define an algebraic function for this as well. I think I mentioned that before. And this is a nice little formula where I have another resistor here. So this is R1, R2, R3. So we're going to say these are concurrent. So I'm going to break this network into discrete nodes and say that this is all just one resistance. And this is all its own other resistance. So I can write that two ways. I can say that V is equal to I times the sum over I of Ri, where Ri is now defined as the resistance at node I. Which for parallel is equal to A harmonic B, and for series is equal to A plus B at that point. So this is the true algebraic formulation of what we've got. This is a generalization of the node law, which we found earlier, and Kirchhoff's law, which is this nice thing here. And we're using those to derive just a nice algebraic form for Kirchhoff's law in general. And this is sort of a given. It also shows us that current at the nodes is always the same. So voltage from the battery is obviously the same. Current then has to be the same, and whatever we change about the circuit is going to be changing the resistances. Okay, so let's talk about, I know that we're running a little long on this one, but I want to now talk about some parallel circuits. So we're going to talk about capacitors in a circuit and inductors. Okay, we have our AC power source, and I want to measure something like how my current is like moving through the system. And to do so, I measure my ammeter here and here, right? So I tell how much current is flowing. I can do it across this. However I want to measure that, I'm measuring it using that. Now, what the current looks like is going to be something sort of like this. So the current's going to go this way, then it's going to get less because my magnet's not turning as fast, and then it's going to turn around, and then it's going to get big. And so I get this sort of time series of measurements, and they approximate a sine wave. So let's draw the current. Now, if I have a fixed voltage for my peak and a fixed voltage for my trough, and V is equal to IR, then as I add resistors, my current is decreasing in the net. So this is measuring the voltage. It's also measuring the current in this case. Now, if I increase R, it actually decreases the amplitude. So I'm going to say if I increase R. Now, that sort of makes sense, right? It's sort of like, I don't want to say damping because I don't want to use that term yet. It means other things, but it is sort of acting like a damper on the spring. Now, if we look at the addition of a capacitor, well, what does this do to our circuit? And that shouldn't be there, so I'm sorry. we'll pretend it has a dielectric in between it. So as long as I'm, relatively close in my capacitance, in the time it takes my capacitor to fill up with charge, to the frequency, then what I get is the current flows this way, fills up the capacitor on that side, and then the current flows the other way, right? The current slows down and flows the other way, and the capacitor, while the current is slowing down, discharges its current this way. So a capacitor can do a couple things. It can either damp or it can act sort of like a phase shift, right? It's moving everything current-wise over just a little bit and also damping it a little. And this is a very general sort of like not great way to think about it, but it's good for the 212 level, which is what we're doing, and that is all that we need for 212. Now inductors, we're gonna look at what the diagram of a current for inductor would look like. So that's gonna be the really fun, interesting one. So I've got my AC power, and I've got my resistor here, and now I've got my inductor. And I'm not concerned with calculating out the parallels and things like that, but this is sort of what you get when you're, you see things like this pretty commonly. So if I look at what the inductor is doing, and this is where we're going to start getting into Lenz's law and inductance, the inductor is creating a magnetic field. Right, so now we're going to introduce a fun new concept, Lenz's law and magnetic field. And you can find this formula, I think, on your formula sheet. You can find it elsewhere. Off the top of my head, I don't want to mess it up a little bit and get anybody wrong. But let me write this here. L essentially resists increase. So capacitors resist change, like we were just showing. L sort of resists increase. So, and it resists the rate. So if I have a current that looks like this, right? And then like this. Let me erase the old current we were dealing with. Then at my peak here, at my peak of my current, come on, my inductor is generating a really huge magnetic field, which prevents my charges from moving through my wire very well. So it may look like this. It may look like, oh, I've got my current, kind of looks like this, so a little bit less this way. And so it phase shifts it a little bit, maybe like that. And then it may do the same thing down here, where the more current is flowing, the more it resists. So you get something that kind of like spikes at the beginning and smooths out a little more. It's not quite a sawtooth. It's more like this. That was really bad, but this is a really good one right here. You get the idea. It kind of like starts and then smooths out. And that's because when I'm at my peak current, I have created a large magnetic field. And that large magnetic field is acting on the charges trying to move through the inductor. So they begin to fail. And my inductor becomes loaded, essentially, with magnetic field. Now, I'm going to erase this. And the true treatment of inductors requires some pretty basic differential equations. It's actually, in most cases, it's a linear homogeneous differential equation. It's just saying that like the rate of change, the first rate of change is proportional to something like the resistance, second rate of change is proportional to the capacitance, and the third rate of change is proportional to the inductance. And you'll see like that as a bunch of slopes, basically. And if you want to dig into that a little further, I will attach probably a link to that in the video of this that I post on YouTube, because it is a great and beautiful subject, that basically everything in life can be a differential equation. So I think we have it today for circuits. Are there any other outstanding questions on how to work with a circuit questions, other than the formula you're given in your formula sheet?
No.
Okay. I'm surprised you stuck around this long. Thank you.
Hmm.
Yeah, if you have any questions, try always the first thing. So let's add that actually as a last step. Strategies for solving circuit. Oh, strategies. So strategies for solving circuit questions. One, redraw the circuit. I always redraw my circuits so that they are facing essentially the same direction, and I see them like a tree branch. So if I have something like this, right, this is a freaking mess, right? It can be solved where each of these kinks is a resistor, but I could also just do this and make sure that it's topologically the same, which means it has the same number of holes. And now, by that subsystem method, ooh, let me undo that one. So by the subsystem method that come on. The subsystem method that we discussed before, this is actually a lot easier to solve because now I have a bunch of little boxes that act like single resistors. Right, so like this is one system, this is one system, this is bigger system involving this system, and I can actually solve for it with a bunch of harmonic products now, instead of solving for it with, you know, I've got to add these and add these and add these, and oh my God, what's going on? This just makes it nice and visual. And if you ever see a circuit diagram, you'll actually see, usually electricians and electrical engineers will start up here or down here and flow this way or this way. And that lets them do things like this whenever there's a change in the flow. You can see it happening. Okay. So yeah, there's a lot of stuff about that. And strategy 2, let's start on strategy 2. Okay. That was redraw the circuit. Strategy 2. So strategy 2 is something along the lines of the node law. So we want to just make sure, absolutely, every time that we have a problem, we want to draw some nodes wherever there's a fork. We want to draw some nodes before and after a component. We want to draw some nodes at one side of the battery and at another side of the battery. And if we're getting, the wrong answer, or we don't feel like it's right, we just want to check the nodes. We want to make sure that the current here is the same as the current here, or the current here is the same as the current here, or the current here is the same as the sum of these two currents, right? So this is a big, nice, easy key to making sure that we're checking our answers properly. So, usually we have these safeguards in the rest of physics where we can check our answer back against something. So like, if I have a block on a plane, I can check to make sure that the friction doesn't exceed tan theta, things like that. Over here, we have this as our safeguard. And a strong safeguard it is as well, because it's a conservation of energy statement. The voltage is the joules per coulomb. So that means that there's an issue of joules in the system, and the energy then is conserved per charge. So that's literally what this is saying. We can derive that the energy per charge is conserved using some calculus. I don't really want to do that. Okay. Yeah, and you said there's no other questions. So those are my two big strategies for this. And I'm going to call that the video.
Okay, thanks.
Yeah, of course. I will turn off the recording.